in mathematics. Please, Pau.
Thank you. Well, welcome to everyone. And so we are talking about the use of equilibrium beach profiles to analyze shoreline changes by the effects of sea level rise. So presentation is based on our study that consisted in revisiting some older models using equilibrium beach profile theory and then proposing an improvement over these models. So first of all, let me talk a bit about beaches. You know that they are very dynamic systems. They suffer the effect of marine forcing, waves, current, there's turbulence, there's interaction between waves and current, there is wind. And also, since the beach bed is not fixed, but it's made of unconsolidated sediment, then it responds to this forcing, and then it changes the shape of the bed. So there's a feedback and there's coupling between the morphodynamics, the bed shape, and the forcing, hydrodynamic forcing. So, for example, if you go to the same beach at the summer and then in winter, or before a storm and after a storm, you may see that the shape changes. So, for example, when coming waves, strong incoming waves come, they tend to, scratch this profile here and generate this staircase, what we call bends, and then it transports the sediment beneath the surface, and then generates this bars. And so then, when another event comes with energetic wave conditions, then waves break here because here the depth is shallow enough, and then they do not break here, so energy is dissipated here, so sediment is not moving. So the message is that it's quite complicated to model all the sediment transport that gives rise to this change of shape. It should be our goal. In fact, there's a lot of people working on this. There's open research, there's a lot of work done, but there's still a lot of work to be done. And so sometimes it's interesting to have simpler models, which we can use to, give first approximations for regional assessment, and also in order to get qualitative knowledge about the system, so we can use later to improve these models. So the idea for equilibrium beach profile theory is the following. If we take this forcing and we freeze it, so we keep it at the same value but not stop it, keep it, then there will be this change, this movement of sediment until a certain point that the beach will reach a state where there's still sediment moving, but the shape of the beach does not change. So this is when the system has arrived to equilibrium. So now if we change the forcing, again, there will be a change of the shape of the beach bed, and again, it will reach a different equilibrium state. So it depends only on the set of parameters that describe this force. So in order to simplify it, instead of taking the whole two-dimensional map, we could take transects perpendicular to the shoreline and average them. So now we are talking about equilibrium beach profiles. So we are interested in this zone, that is the one under the effects of incoming waves and other marine forcing. So this is what we call the active profile, where this forcing is capable of changing the bed because of sediment mobilization. So it starts to what we call closure depth. When sediment starts to be mobilized, then waves break, then they are up to the shoreline, and there's still a zone, as we were talking before, where they can still change the shape here. And there we have another shapes, but these are not generated by waves and currents, but wind and other effects. So we are interested in this field. And then in the equilibrium, we said this shape here only depends on a set of parameters. So also the volume enclosed, the area enclosed by this profile, is on a function of the parameters that can be used, this piece here, to describe the equilibrium state. So this is a state function depending on these variables, which means that if we know these values for the forcing, then we can know the state and the shape and the volume enclosed in this profile, and we don't care about the path, how the sediment has moved to arrive to this state. So this is true as we consider that we are not facing quite extreme events, but in general it might be an approximation. So the idea to use now, using this theory, is instead of modeling and parameterizing the actual flux of sediment, is taking two snapshots to two cases for fixed forcing. So, for example, the forcing that we have today, and then the equilibrium that we will have today, and also the equilibrium of, let's say, tomorrow. So we can subtract the two shapes, and then we know at which places there has been movement of sediment, and also if overall there has been a change of the total sediment volume, but without needing to parameterize this movement. So this idea has already a few years. Actually, the one that used the idea of equilibrium profiles to model this change of Shoreline was Brun in the 60s. How he assumed that for changes in mean sea level, this is the slow change, is not the fast one associated to stones or something like that. For this small slow changes, of sea level, then the equilibrium profile will lift with the new conditions, and then since we need sediment to move the profile upwards, then it should go backwards towards the land, and then the sediment needed to lift the profile will come from this landward movement. So he assumed that there was no change in the profile, and also that no sediment was exchanged to this system. So, for example, for beaches at the river's mouth is not the best approximation, but for most of our beaches it will suffice. Then later, Edelman in the 70s, he also proposed to use the same idea, but he instead was interested on analyzing what happened before and after a storm. So now we are not dealing with mean sea level slow changes, but with still water level, which is the horizontal change of this level. And he assumed that since the time scale of a storm is not fast enough to change the overall profile of the emerging part of the beach, it will remain the same. So the idea is the same. We have a proportionality between changes in the shoreline and changes in the sea level. So for a certain sea level, depending on the ratio between the width of this active profile and the height of this active profile. But for Brun, since the whole profile lifts, then the ratio was not changing. But for Edelman, since the emergent part of the beach was not lifting, but the bottom part was, it starts to get smaller. So when this event advances, then this erosion becomes more pronounced. It means that the same change in water level affects more when this profile is small. So then in the 90s, Dean again used this idea and also added information on the effects of sea levels that were not flat, adding the effects of wave setup. And the interesting part here is that he considered instantaneous wave conditions. So for these two models, they considered conditions that were representative of extreme waves. So they ensured that they considered all the profiles that could be moved in general. But he said that it could be also be done for instantaneous conditions. But there are too many problems. Sorry.
Can you explain again what's the difference between delta YS and DYS?
Yes. So this is what Brun did. Sorry, that was something that I was going to say now, but I think now. So what Brun did was to compare two states, what the beach will be today and after, let's say, 100 years. So it compared them, and then he did an approximation. So it depends on the shape of the profile. Some people say that it only can be used for monotonous profiles, or there cannot be bumps or this kind of bars. So it's meant for finite changes. But what Edelman did was to consider, since they were so fast, they considered small changes. So for the reason I used infinitesimal changes instead of finite changes. But again, all three models, and general the models, are approximated. So they depend on a prescribed shape for the depth, or small sea level changes compared to the height of the profile. So they have a series of assumptions that make this application a bit tricky. And also, there's an even bigger problem with all these models, and is that there's a lot of ambiguity of which width and which height should we consider for these computations. So depending on which author do you consider, and even if they applying Brun's rule, this model, for the same beach and the same data, they can give different answers because they consider different profiles. So Some people say, let's consider from closure depth up to the dune toe. So when this zone begins. Others say no, and let's consider when the berm begins. Others say no, let's consider from the shoreline. So there's no consensus about this. And therefore, results are different. So our idea is to take what we think all the ideas are here, all the best ideas, so this conservation of sediment, the idea of using infinitesimal steps, using instantaneous conditions, all the ideas are there, but need to be combined. And also, we need to provide a general a model general enough, so we can be strict and give a precise definition of which is the zone to be considered. So this is our idea, okay? The idea is to have a model in 4 parts. We don't care what happens here and here, but for the active profile, we need to have a part for the subverted part of the profile, which responds vertically. So if we have the water level, and then responds horizontally. So this is what we have the displacement here, and also the same for the emergent part of the active profile. And then the shapes, however, can depend on a set of parameters. So the idea is to follow the same idea of an Edelman and to take infinitesimal difference, so we can create changes of this as a sum of changes in each of the parameters, which is modulated, but how much a change in this parameter will cause a change in the decimal model, plus saying a change with the models. So again, we consider that this is 0, so we are moving on an ISO line, on an isosurface of this function. So knowing all the forcing, we can compute the changes in the shoreline. So, this should have color, but I think that I was not prepared for the projector. But the idea is that here we have changes that correspond to elevation, vertical movements of the profile. This other term that corresponds to horizontal movements of the profile, also changes in the width of the profile, and finally, changes in shape, distortions of this profile. So in order to simplify it for this presentation, although we can remain the whole model we're doing in the study, what we can do is to assume that the profile is continuous. So if the profile has no discontinuities, then we only have the terms corresponding to changes, movements of the profile, and distortion. If we also consider that there's no change in shape at all, so we would retain only the term that it's interesting for us to compare with other models and to get the base idea of this formulation, then we arrive to this condition here. Again, we have the same result, but now we know which are the dimensions that we need to consider, and also, in this case, we know that we are not limited to a specific shape or to any of these conditions that were the other formulations approximate. And also, if we could use the other terms. We could add them. But we need to be cautious because we can have 2 different cases. So if the beach is wide enough, so this range of marine forcing in the emergent part of the beach is smaller than the actual width of the beach, then we recover the same expression down below. So this is that the changes in beach width, shoreline, they are the same, are proportional to changes in mean sea level. But the constant of proportionality is again this ratio of the width and height of the profile, but considers or should be used, average conditions, not the extreme ones. So sometimes the ratio of the profile will be bigger than the average, and sometimes it will be smaller than it. But in general, the actual rate of erosion will be that given by average wave conditions. But then, if beach is not wide enough, then the actual range of action, the zone that can be affected by marine forcing, is bigger than the actual beach, the actual beach width. And so we only, for the active profile, we only have this element here. We cannot consider the potential with that. So this parameter here that controls how gets modulated a change in sea level to a change in beach shoreline or beach width displacement depends on the actual variable that we are trying to solve. So it gets more complicated. We have some tentatives, but we are still working on it. We have still a bit improvements to it. But for presentation purposes, let's assume that we can do the same idea here. Here we have a linear equation, so let's assume that we can decouple it, and we can write here also only in simple to show you that things change. So if we consider this coefficient here, that is what indicates if a change in sea level will give a big change in shoreline position or a small one, we have plotted. So you see that when beach is wide enough, it's constant, but when beach starts to get narrower, it starts to change. So it means that now beach responds differently to the same amount of sea level rise. So now if sea level changes, let's say 1 meter, then the beach shoreline will go slower than it was already before. So we have to take into consideration this change in behavior of the beach. And now let me present 2 examples that we have created for the comparison of all the models. Okay, so we are comparing the models I have presented, Brun, Edelman, and Deans, with the model I just showed you, and also with a numerical model, considers the morpho, which is also based on equilibrium profile theory, but that incorporates sediment movement. So we are not saying that real beach will follow this exactly, but if we are inside this formulation of equilibrium profile theory, then what we obtain should be the most similar possible to quasi-morpho results. Okay, so these quasi-morpho results, which are our reference, say it again, its mean of evolution is this red spiky line, and then its range by minimum and maximum is this headed table. And then we can see the evolution predicted by this model, Brun and Edelman, and our model. So this was conducted by assuming a sea level rise, a parabolic sea level rise of 1 meter, combined at the same time by high frequency forcing provided by Tim Hankas, that he presented in November, right? Yes. So you will see that we have 2 lines here for our model. One is what we obtain considering this proportional model, assuming that the beach is always wide, although it's not. And then the green one, that presentation purpose model that uses a wide beach model when the beach is wide enough, and then uses this simplification, this decoupling of the equation when the beach is not wide enough. So you can see this model goes quite far compared to other ones, and that's because first he did not consider the emergent path of the active profile, and also because he uses average conditions, but at the breaking point. So then we have Brun and Edelman. Edelman is just a higher correction of what Brun did. And in this case, they are also not considering the emergent path of the active profile, but since they use extreme wave conditions instead of average ones, they provide a greater evolution than what Dean says it will be. And then our model that follows the quasi-morpho results quite well. And here we have a narrow beach. So this one started at 60 meters wide, and this starts at 30 meters. So now we can say that there's a difference between the always wide model and this mixed model. So I was expecting this narrow model not to follow the quasi-morpho results because it does not incorporate, it does not solve the narrow model correctly. But what surprised me is that actually the quasi-morpho results that we use as a reference seem to be more in common with the wide beach model than with the, although simple, narrow beach model. So this is the point that we still have to solve. So to end, again, we should use sediment transport in general, but for those cases that we are interested in using a simple model, so equilibrium beach profile theory, we should have in mind these points. The first thing is that we should use infinitesimal steps and then integrate them in order to provide results the most accurate possible within the field. And then it's important to take into account the emergent part of the active profile and also instantaneous, which result in average wave conditions instead of extreme ones. And finally, that although we still do not know how the beach behaves when it becomes narrower, it's important to consider that it behaves differently, and it may change what happens when the beach is wide enough and when it starts to become quite narrow. It's something that may happen soon with sea level rise. And that's it. Here you have my important information. So we'll discuss this. I don't know. Maybe something. Thank you. Any question? Yes.
Can you please go back to the equation of the active profile?
Yes.
The surface.
This one?
Yeah. I was expecting that the differential of the area would
Yes.
be positive because of the sediment accumulation, or maybe negative. I don't know, but why is it zero? I understand it's for solving the equations, but why do you?
So the idea is to use this when we believe there's no significant change in the sediment volume that is within the beach. So for these cases that we expect there are changes in this amount of sediment, for example, these beaches at river mouths or that are losing sediment, or that because of longshore transport can give can receive more sediment or lose it, then there are formulations which also add a term of a flux of sediment entering or exiting the profile. But since we were wanting to compare with previous models for this presentation, we did not add it. Also because in our region, not so crazy to assume this conservation of volume, because we don't have rivers, and our sediment is usually generated locally. We have a lot of beaches which are enclosed, so it's a good idea for our region.
Actually, it was one of the questions that I wanted to ask. So your models, the way you massage your problem is based on two assumptions, if I'm correct, right? One is the conservation of the area there,
Yes,
which you touched upon, and the other one is the fact that the shape of the profile doesn't change with in a sense the distortion. What
yes,
and well that you were calling
yes,
distortion before is negligible, right?
So
I mean, is there actually something that is born out of the experiment? Or actually, are there experiments on this?
well, you see, the model could have it. So we have this, and actually for wave setup, what did I was talking before to wave setup, that is this distribution of sea level along the profile. So we can model as a distortion component. So we could have shapes that depend on profiles. For example, that become steeper when there's different wave conditions. Depending on the wave height, it can change its slope, for example. So we could use them, and it can be easily incorporated into the model. But for this analytical, let's say, comparison point, it's not of interest. Also, it depends. Usually people tend to use these profiles that only depend on sediment grain size or these parameters which are constant within the shape. So it should depend on the incoming forcing shape, but it usually is not studied like that. I think, although I'm not sure, that since we are interested in sea level rise, which is a slow, have this slow time scale, considering this profile, which can be more or less representative of average conditions, again, is not that bad approximation. It could be some coupling between, but let's say that it's less prone to be risky for sea level rise than for fast changes. So, for example, changes of level depending on tides or storms or waves.
But because essentially what you have, if I understand well what the parameters are there,
Yes.
what you have in the DYS equal blah blah is essentially you're saying that the tangent of the angle there is a constant. And you're just moving back a certain amount because they see that on the right.
That's the point. Yes, you're considering the secant between these 2 points. So you are yes.
Okay.
That's the point. But you could consider also changes in shape. So you can use a profile that does depend on the parameter, and then just it will be another term. So that's the point. It will be another term in the derivative because we are considering these small changes. So it's a linear extension.
And a follow-up question that I had, is there a role in the possible presence of vegetation?
Sorry?
Of plants, for example, in the shore, just in the area, in the part of the.
Well, it could. We have not considered them. It could be an effect, yes. So if they are deeper than this heavy mobilization, it's no problem for us. But if they are in this zone, yes, we should consider like this. For example, they can fix this height. For example, can give some effect. Yes.
Can you include it in your numerical model, this instance?
You're being into quasi-morpho?
Yeah.
I don't know. I think it's not still ready for these things. I would ask it because I'm not the one who developed the numerical quasi-morpho, but you could use other, for example, I think Beach does have it, maybe. Or I mean, there are other models too, not for these time scales for sea level rise, but for faster or shorter events. Maybe there's some others that do incorporate them, but they're all numerical one within this approximation. Yes.
Because here it's very trendy to see if that's good or no. I mean, it does have an effect. So yeah, maybe because in Mallorca you're working, in Balearics you're working with this kind of fish.
Absolutely.
It
could have an effect.
But yeah, if you don't have the reference compared to the ground truth.
Yes. Yeah. So it could be a bit of work. Yes.
Yeah, good question or a comment. More
yes.
What you kind of question. I don't understand what you do. You try to simplify everything better. One of the things that I see is that we are considering actually that okay, when the program has to adapt, you have like a donor zone in the dry area. One of the things is that most of those models, etc., are assumedly, or not assumedly, they actually are based on a unimodal distribution of sediment grain. But when you introduce the dry beach, chronometry over there is very different to what you have the profile. So your donor sand or your donor sediment is different than the average sediment you have for the profile. I don't know what's there or that this can introduce over there. I know you didn't have it addressed that, but I would like to know your opinion. Just
well, usually what I have seen that they do consider that sediment size or sediment type affects to the shape of the profile. But of course, there's a distribution of sediment, of the sediment, depending on the part of which we're talking about, you said. So yes, it could be that the sediment that enters by this zone has not the same effect that the sediment that is here. I don't know right now how can we model that, or even if we could model that with such a simple model. But yes, again, like with the Posidonia thing is something that that can be considered or should be considered by more complex models.
Well, I don't think it's that complex anyways.
Yes.
Because I would say that normally the sediment you have in the dry beach is coarser than the other one. So if you are assuming that the volume from there is going to the rest, it's just over the time. Oh, if you work it over the long time, that is going to change slightly your distribution of sediments towards a slightly coarser sediment. So that would give you a steeper profile on average stems on the long term.
Yes. So you could consider it as a changing shape then.
Yeah.
So if your profile depends on the sediment size, you could use like this distribution, and assuming that it changes depending on the fraction that is entering here. So you could change this, let's say, distribution of sediment, and also update this characteristic sediment size that you use for the shape. It could be a way, totally. Yes.
Very basic question. How do you define this actually?
Yes, so for the submerged part of the beach, we usually consider the I don't know how to say in English, the critic stress, that's it, for sediment mobilization. So you consider which is the minimum force at the bed of the beach that you need to start to mobilizing sediment. It depends on a set of parameters. There are different parameterizations to that, and then usually it's computed as a fraction of this depth or a function of that depth. So you depending on the incoming waves, usually most of all it's height, and sometimes also its period. You could compute this instantaneous critical stress that you need to start sediment mobilization, and then compute this depth here. Once you know this depth, since you know the shape of the profile because it's defined by your parameters, you could know also this width here. So for the emergent part of the beach is trickier because it's not as clear as that. Usually, well, you could consider the effects of swash, for example. So to see which is the let's say the land most wet area. For quasi-automorpho, I since we are comparing with quasi-automorpho, I use the same preference that it used. So we could compare with that. But if we are using this for a real beach, we will need to characterize this size, at least its average size. Yes.
You said with the swatch?
Yes. So since we are talking about the range that is affected by waves and general marine forcing, so you will consider the maximum, the landmost point that is still touched by this.
And from what do you compute the swatch?
So since you have the incoming forcing conditions, for example, I use your Hencas, so I could compute it parametrically.
Like with the stop or something. And the depth of closure are the same.
Yes, it has a different formulation, but again, it's computed using the incoming wave conditions. Yes.
It's a big measure or alert measure?
No, because those are used to compute this extreme wave condition. Because Birkemeyer and Haller-Meyer, they are formulations that give you the closure depth that is consistent with waves that are only occurring. So waves that are stronger 12 hours in the whole year. So they did so because this way you could consider more or less the whole profile, but sometimes it's smaller. So there are formulations that, depending on the instantaneous wave conditions, tell you which is the depth at which sediment mobilization starts. So this one actually is changing in our model. This one is not, because we don't have that parameterization. We could use swatch, for example, but since we are comparing with quasi-automorpho, we use parameterization just to avoid more uncertainty. Yes.
One question I'm understanding, over time this zone is it moving? Like if we watch from a fixed angle or from a fixed position, the zone is it moving the land inwards?
So the profile, you mean, or this point here?
The profile.
Yes. So the idea is that it's
In the y direction, right?
yes. So the idea is that it adapts to the instantaneous. Since it's equilibrium, it will take longer to occur actually in the reality, but for the theory, since we are considering the equilibrium one, it changes depending on instantaneous sea level and the Shoreline position. But yes, the idea is that it moves, it may change shape, although for this presentation we don't consider it, and it just adapts to the new position of the shoreline, let's say. Yes.
And it's definable if you use to have like a map, for example, open up an island like Mallorca to see it over time the beach width on a satellite image or
The problem is that, changes associated to sea level rise are quite small. So we try to use satellite data to validate these changes, but the high frequency effects caused by waves and storms completely, I mean, the changes in beach width that they generate completely mask the effects of sea level rise, actual rates, and at satellite pixel scale, at least. Yes.
So I don't know, maybe it's just something completely irrelevant, but so in the green area there, which is the area that changes, right?
Yes.
You assume that the material is all uniform, but I don't know exactly how many meters would we be talking about in terms of depth, but what if there is a rock bed or something like that inside? How is that going to change does it change anything?
So you need to parameterize again as a distortion shape. So you cannot go deeper than this point at this moment because there's a rock. So for this simplest formulation that we presented, you don't do it because you show me all sediment. Again, since we are talking about sea level rise, it may be more problematic than if we were talking about sinking the level. But yes, it's not considered right now, but you consider again as a distortion effect. So if since you consider sediment size to define the shape, you could also consider the position and height of a rock and width of a rock to consider that the profile cannot go under that. So this is the analytic solution that we were developing. The last one that was interesting to give an idea and to get insight about that. But this differential equation, although simple, can be solved numerically. So if you incorporate these complexer parameterizations, it could be solved numerically. Yeah.
But the rocks also have, well, it doesn't matter. We can discuss it. Maybe the rocks have a yield stress that might be different from the granular material, the wet granular material that is considered there, right?
Yes, but again, this only considers.
And then they transmit stress a different way, and so there must be also an influence in the shape.
So you mean that the rock shape may change because of the sediment weight?
No, what I'm saying is that pushing on a rock,
yes,
on the piece of rock that is protruding, is not the same as pushing on horizontally,
yes,
on the piece of wet sand that is then pushing on the rest of the wet sand.
Yes, but again, the thing is that this theory does not consider the dynamical effects needed to do this thing. You just consider that if the rock is there, you just model its shape. That's all. Because what you do here is just to compare the shape of one profile and another profile. So if there is a rock, you do not need to worry, at least in this theory, about the nature of the rock itself, just its shape and its position, and that it does not change. So if also, however, you need to consider that it does not give sediment to the profile. So when computed these things in elevations, you should be careful. So it should be incorporated somehow that this movement of the profile does not give sediment volume to the profile. That it's indeed a problem. Yes.
Also, one very basic question for understanding: how do you measure the profile in the experiment, or where do you get data from the profile?
Okay, so
which is the measurement devices?
So usually there's a person. So in reality, what we do is just going with a GPS and moving, or with a boat and with a sound, echo sound.
Yeah.
Or well, now people use even boats like toys, but drones that remote with an echo sound. But usually is for the shallower part you are moving with a GPS, and from the deeper part it's kind of a boat with an echo sound. So actually this parameterization of profile that, for example, Dean and Brun used are based on actual surveys that were done on the field.
Can you scale this kind of up, this measurement in the future? What do you think?
So what do you mean?
Like to scale, because to walk the whole beach with the GPS takes a lot of time.
Yes, so that's
And
the
also
problem.
the underwater is maybe even more complicated than the.
Yes, so actually the problem that we have in our field is that data is, in general, data is quite precious, but here our problem is that for measurements we need to, I mean, it's not as easy as doing like, I don't know, other kinds of research that you can have your measurements in the lab done. Here you need to go to the field and spend time, and if there's a storm, then well, it changes the shape completely. You need to go again. So there are groups that are actively monitoring and surveying their study sites, but there's also a lot of work here. For example, now what I'm actually doing in my PhD, it's not supposed to be on this, but on measurement of these variables using remote sensors. So for example, for underwater bathymetry, what we call a bathymetry, underwater elevation map, people use video cameras, because if you are watching the incoming waves, the period of the waves and the space between the crests, so the wavelength and the frequency, define the depth because of wave dispersion equation, define the depth in there. So you are monitoring the waves and can know the depth beneath it. There are also other methods. For example, for the emergent beach, people use LiDAR also, but not spaceborne or airborne. Also airborne sometimes, but usually, just in a building next to the beach. People is also using radar to measure shoreline. Shoreline can be also measured with video. So our idea is to improve these measurements using this remote, but not too remote measurement.
Anyway, just to remind you, you have experimental channel out there in the parking lot.
Yes, the problem is that
Very perfect for drone.
absolutely, but we work with waves. But yes, we will be very interested. Absolutely. Yes.
I'm a biologist, so I don't have the best knowledge on this, but I know that sand is like, it's not a solid, it's not a liquid, it's like a fluid in non-Newtonian.
I'm not sure about it. I didn't have my soft math physics. Sorry.
I'm thinking like how the brain size, for example, the porosity, the thickness, on the nature of the brain by itself, even the chemical, will have an impact on the shape of your surface. Do you
Absolutely.
consider this, or?
Absolutely. So we were discussing with him that, for example, the characteristic segment size makes the slope of the profile different. Also tend to be distributions of the different materials. Also, depending on the shape or the characteristic of the material, actually the slope is different because it's not only the size of the segment, but also its setting velocity. So there's actually there's a lot of dependence on the sediment nature, not only its size, but also material shape. Yes, absolutely.
Mobility there depends, like the mobility everywhere. The critical mobility that you were defining there depends on the dimension of the.
Yes. Depends. It depends. So we consider for this result that we presented, we considered a characteristic sediment size for a beach that we know in Menorca, and we just used it. But again, it should be depending on the nature. But we use the parameterizations already available. So I'm conscious that this is a very simple one. So it has a lot of credits, but yes, it's quite complex. That's why we use this simple thing instead of complex. Yes.
And so the segment size, particle size is a parameter in the model.
Sorry,
The particle size.
Yes, it is
a parameter, but there's no other material parameter like the shape or
the. It depends on which formulation you consider. So, for example, for critical bed mobilization, I think it only depends in the sediment part, not in the wave part. It depends only on the characteristic size.
Yeah.
For the shape of the profile, usually those are based on setting velocity. So setting velocity depends on also in I think it's the elasticity of the. So it's not only the size, but there are other factors that depend on it.
Okay.
But
this setting velocity includes already these factors, kind of.
Sorry?
You have a sampling velocity as a empirical measurement,
Yes, yes.
and that's good enough, I think.
Usually the parameterization available are based on setting velocity. So if there are other effects that are not considered, they are subsumed in this parameterization.
I mean, it's also good if your model doesn't contain too many material parameters, because it means you have to determine all of them. And if setting velocity is a good one that includes
Yes.
everything you need.
So it needs to be calibrated somehow. I mean, we cannot expect what happens with the whole width without knowing it. But the idea is that we need far less parameters than a complex parameterization, which requires more information on the sum distribution and in other effects. But yes, you need some information about the bits, totally. But usually is obtained by experimentation. So either you take a sample of the sand, or you consider the usual sand characteristic of your region that are usually known. But yes, you need information.
Good.
Well,
Okay, thank you.
thank you.